We start with this video with a problem. Mass of a uniform rod of length 10 meters is 10 kg. We take a uniform rod. Now the mass is 10 kg, that means the weight of the rod is acting at the center of the rod, just at the center of the rod, that is 10 kg. 10 kg or 10 into g. The rod is placed over knife edges A and B. One end of the rod is resting on the knife edge A, and the other end is 2 meters outside the knife edge B. Other end is 2 meters, that means this part has a length of 2 meters. Other end or end, you can name it C. This is A, this is B. So the fulcrum rests at one end A, and the other fulcrum is 2 meters inside the other end that is at B. A 30 kg weight is now suspended 2 meters away from the end A. So this is end A. Now 2 meters from the end A. So this is 30 kg weight. This is also a length of 2 meters. Find the magnitude of the normal forces on the knife edges. So on the knife edges, normal forces, suppose this is R1, suppose this is R2. Now the length of the rod was 10 meters. Length of the rod was 10 meters. So this is 2, this will be 3 meters. And if this is 2, this will be again 3 meters. So for the conditions of equilibrium, from conditions of equilibrium, the first condition was summation of the forces was equal to 0. So we try to find the equation. R1 and R2 are acting along the positive y-axis, so R1 plus R2, and the weight acting downwards, that is 10g. Also the 30 kg weight is also acting downwards, so that also gets subtracted. So R1 plus R2 is equal to 30 plus 10. We can write R1 plus R2 is equal to 40g, or 40 into 9.8. You can also do it with the value of 10 for g. This comes out to be 3920. So 392 newtons. Now another condition of equilibrium was summation of tau must be equal to 0. Now summation of tau, this is a very important thing to learn. First one is, we have to take the moment about a point. Now there are so many points. We can take the moment about point O, you can name this a point as suppose D. We can name this point as O, this is B, this is C. We can take moments about or with respect to any one of the points. So let us take the moments about the point A. If we take the moment about the point A, then the moment of the force R1 becomes 0, because R1 is acting at A, hence the perpendicular length or perpendicular shift is 0. So we try to write the equation, that is R1 into 0, because R1 is straight acting at the point with which we are taking the moments about. We can write with respect to point A. In the examination paper, you have always to mention this thing with respect to which point you are taking the moments. So R1 into 0. Now this is a 30 gram weight. So 30 gram weight, 30g into 2 meters. But this 30 gram, it will try to rotate the rod or the rod in the clockwise direction. So this must have a minus sign in front, not plus. It must have a minus sign in front. Because if this point is the axis of rotation, then B will try to rotate the rod in the clockwise direction. Another force is 10g, that means the weight of the rod. Now also that force also will try to rotate the rod in the clockwise direction. So minus of 10g into distance of 2 plus 3, that means 5 meters. Another one is R2. Another one is R2. But R2 will try to rotate the rod in the clockwise, in the anti-clockwise direction. So it will have a plus sign in front into how much distance? 2 plus 3 plus 3. 6 plus 2, 8 meters. So these are the forces, 1, 2, 3 and 4 forces, out of which R1 will be 0 and the rest 3 will have the respective moments about point O. That must be equal to 0. That means R2 into 8 is equal to 294g, 294 into 2 plus 98 into 5. This is G is 9.8, so 9.8 into 10 is 98. 98 into 5, moving on to the right hand side, becomes 98.5. This is 60G. So 60 into 10, 600. 60 into G, 9.8. Have to check it. So this will become 588 plus 98 into 5 means 98 into 5. 490. Now 490 plus 588, 1078. 1078. So R2 will be equal to 1078 divided by 8 becomes 134.75. 134.75 newtons, and R1 must be equal to 392. The sum of the two forces was 392 minus 134.75. So 392 minus 134.75 becomes 257.25. 257.25 newtons. So this is the value of R2, this is the value of R1. Now after this we are going to discuss about the equilibrium condition in a two-dimensional plane. That means for a ladder, the basic concept is, if this is the wall and the floor and we are placing a ladder with an angle of theta, yes, suppose this is the wall, this is the floor. Now for testing the equilibrium conditions for this case, we can take number one, summation F is equal to 0, but the forces acting on the ladder will be along the x-axis as well along the y-axis. That means it's a two-dimensional form. So we have to split this first equation into two equations. First equation into two equations. One is summation of fx is equal to 0. That means the sum of the forces along the direction of x will be 0. And another one is summation of force along the y-axis will be 0. So this point has to be split up into 2 points. And second one will remain the same. Summation of tau must be equal to 0. For this one we have to take with respect to some point O or point B, point C, something. Now let us talk briefly about the forces that can act on this ladder. Now if the ladder is slanted here, there will be a reaction force from the wall on the ladder. Suppose this be R1. There will also a reaction force acting on the end of the ladder or the foot of the ladder from the ground, that is R2. The basic minimum is the weight of the ladder acting at the center and acting downwards. Now if there is friction force on the wall as well as the ground, the top of the ladder, this tip, will try to force himself downwards because of this weight. This tip will try to force downwards because of this weight. So a frictional force will be acting in the upward direction, preventing the fall of this tip. So let this be small f1 is equal to mu r1, because here the reaction force is r1. Similarly, if this tip tries to move downwards, this end will move in the leftward direction. So if this end moves in the leftward direction, the frictional force acting here will act in the inward direction. That is, F2 is equal to mu 2 R2, where mu 1 is the coefficient of the ladder and the wall, and mu2 is the coefficient of friction of the ladder and the floor. So this can be the kind of forces that can act on the ladder. We take one or two examples to understand the style of problems. So we take this example. This states that a ladder weighing weight of ladder is W. Rests with one end against a rough vertical wall. This wall is rough. That means frictional force acts on the ladder, and the other end on a rough floor. This floor is also rough, so frictional force also acts. It is inclined at an angle of 45 degree with the horizontal. So this angle is 45. Coefficient of friction of the ladder with the floor and the wall are mu and mu dash. So here it will be mu and here it will be mu dash. Show that the minimum horizontal force. Now the question is, show that minimum horizontal force that can move the base of the ladder, that can move base of ladder. That means this base towards the wall, is W into 1 plus 2 mu minus mu dash by 2 into 1 by mu dash. Now this question has a very important term in it, so that the minimum horizontal force that can move the base of the ladder towards the wall. Now we take the minimum amount of force to be F. Suppose this is the amount of force to be F. We are trying to move the base of the ladder towards the wall. We are pushing the base of the ladder towards the wall. What is the minimum amount of force that is needed to move the ladder? Now, as explained in the previous diagram, we can take number 1, summation of Fx is equal to 0. Summation of Fx is equal to 0. So from this we can write that in the direction of x means F r dash and the frictional forces. Now the frictional forces here, if we push the ladder in this direction, the frictional force will act in the opposite direction of motion. That means mu r will be acting to the leftwards, and the frictional force, if this force is applied here, this tip will try to move upwards. So here the frictional force will act downwards, mu dash r dash. This tip, I am pushing the tip towards the wall, so this tip will try to move in the upward direction, as frictional force acts in the opposite direction. So frictional force will act at this point in the downward direction, and its magnitude will be mu dash r dash. Now summation of Fx is equal to 0, we can write, if we take F to be plus, that means along the positive x direction, that means r dash will be minus in the negative x direction, as well as mu r in the negative x direction. So from this we get F is equal to r dash plus mu r. Second equation. What will be the second equation? Along this line, y axis. So W is acting downwards. We can take that to be minus W. R is acting upwards. We take that to be plus R. And mu dash r dash is also acting downwards. So mu dash r dash is also along the negative y axis. So W plus mu dash r dash must be equal to R from this equation. Let the points be A, O and B. Now AO is equal to OB, because this angle is 45 degree, this will also be 45. That means AO is equal to OB. Let us take this line to be suppose 2L, BO to be 2L. So you have to try to find the moments of this ladder with respect to point B. Now there are 3 points with which you can take the moments about. Number one is B, number one is G, number one is A. At A, two forces are acting. At point G, one force is acting, and at point B, three forces are acting. So it will be very appropriate to take the moments about this point B. Take the moments with respect to B, because there are three forces here. More the number of forces acting at a point, the more the number of zero moments we'll get. There are three forces, so three forces will have no moments, and the equation will shrink. Equation will be shorter. So we can take the moments about point B. So third one is summation. I have not written it here. For this condition, it is summation if y was 0. Now summation tau is equal to 0. With respect to point B, what we can write? We take the moments about r, mu r and f, all are 0. And this w with respect to point B means the length of this part will be L. We have taken this total to be 2L, where W, the line of action of this force, passes through the midpoint of BO. So this part will be L. So W into L. W into L. Now W into L, this will try to rotate in the clockwise direction. So it will have a minus sign in front. Now again, we take force, suppose mu dash r dash. Now mu dash r dash, the line of action of mu dash r dash is at a distance of 2L from B. So mu dash r dash into 2L. Mu dash r dash into 2L. Now mu dash r dash into 2L will also have a negative sign in front, because it is trying to rotate the ladder in the clockwise direction. And what remains is r dash. So r, line of action of r dash is this one. So the distance of the line of action from the point B, it is 2L. So r dash into 2L. Now this will have a positive sign. R dash into 2L is equal to 0, because r dash is trying to rotate the rod in the anti-clockwise direction. So it will have a positive sign in front. From this equation, we will be trying to find out the value of W. This will be plus, let us first write in this fashion, W dash R dash into 2L is equal to R dash into 2L. So W is equal to 2R dash 1 minus mu dash, or R dash is equal to W by 2 into 1 minus mu dash. Now from the equation, from this equation we can get the value of R. This was the equation. R is equal to mu dash R dash by W. In that equation we replace the value of R dash. So we get the value of R as W into 1 plus mu dash by 2 into 1 minus mu dash. And replace this into the first equation. F is equal to R dash mu R. This was the first equation. This was the second equation. We have taken out R dash out from here, got the value of R dash, replaced it in the value of in the equation 2, in this equation 2 to get the value of R. Now we replace R dash and R both in equation 1 to get F. So what will be the value of F? W into 1 by 2 into 1 minus mu dash plus mu dash mu by 2 into 1 minus mu dash. If we solve this, we will get the required relation to be proved. Mu dash by 2 into 1 minus mu dash proved.